Morning. Good morning, everyone.
Good morning, sir.
Good morning. మీకు ఈ క్లాస్ చెప్పలేదమ్మా ఈ టైం అని 8:30 అని.
No, sir.
ఓకే.
ఇప్పుడు చెప్పారు సార్.
ఇప్పుడు చెప్పారా? అది నిన్న డిసైడ్ చేశారమ్మా మీకు చెప్పడం బై మిస్టేక్ మీ హెచ్ఓడి లేట్ చేసినట్టున్నాడు.
ఓకే సార్.
ఓకే. No issue. Ask them to join the remaining people also, please. Okay. Today we are going to discuss about adjoint of a matrix. What is adjoint of a matrix? The transpose of a matrix is replaced by its cofactors is called adjoint of a matrix. That is nothing but let A be a square matrix of order n. The transpose of the matrix got from capital A by replacing the elements of A by corresponding cofactors is called adjoint of a matrix. For any scalar k, adjoint of Ka is equal to k in k power n minus 1 into adjoint of A. This is one of the resultant of the adjoint. Now here, suppose for example, if A11, A12, A13, A21, A22, A23, A31, A32, A33 is a 3 by 3 matrix. If you transpose this matrix, that means rows into columns and columns into rows. That is vice versa. After getting that transpose, the transpose of a matrix is replaced by their minors, the cofactors. That means that minus 1 power I plus j into mij, where I equal to 1 to 3, j is also 1 to 3. Replace that values with cofactors, we get adjoint of a matrix. This is already known to you. It is from 10th class to up to your intermediate. We have some knowledge on this adjoint of a matrix, but we have to remember that result if k is a scalar, adjoint of k equal to k power n minus 1 into adjoint of A. Because if you obtain the cofactors, if n is the order of the given matrix or the size of the given matrix, then if you obtain the cofactors, we get order k power n power n minus 1 power size n minus 1. That's why we get k power n minus 1 into adjoint of A. Next, we want to discuss about inverse of a matrix. Let A be any square matrix, then there exists another square matrix of same order such that AB equal to BA equal to I, identity matrix. Post multiplier and pre-multiplier both are exists and which are equal to identity. The product of the two matrices equal to identity matrix. If this condition is satisfied by any matrix B, such that B is called inverse of a matrix. So inverse of a matrix B is notated as A inverse. A inverse. That is nothing but B equal to A inverse. That means that A into A inverse equal to A inverse into A equal to I. If this condition is satisfied by any matrix, that matrix is itself is called inverse of a matrix. A inverse whole inverse equal to A, that's all. I inverse is equal to I only. O inverse is equal to O only. That means null matrix, inverse of null matrix, inverse of identity matrix are same as this matrix itself. Next, the necessary and sufficient condition for a square matrix to possess inverse, the determinant of A is not equal to 0. Here, based on this, determinant of A is either equal to 0 or not equal to 0. We come across two types of matrices. One is singular matrix, another is a non-singular matrix. If the determinant of a matrix is equal to 0, that is called a singular matrix that has no inverse That type of singular matrix has no inverse matrix. Next, if A is not equal to the determinant of A is not equal to 0, that means the determinant of a matrix is not equal to 0, then that matrix is called non-singular matrix. Non-singular matrix. Based on this, determinant of A is not equal to 0, we have a formula for A inverse equal to adjoint A by determinant of A. If determinant of A is equal to 0, then this is not exists. If determinant of A is not equal to 0, then A inverse equal to adjoint A by determinant of A. So if you want to find literally A inverse by using the traditional method, first of all, we want to obtain adjoint of a matrix. What is adjoint of a matrix? Adjoint of a matrix is nothing but the transpose of a matrix, the entries of the transpose of A is replaced by its cofactors, corresponding cofactors, we get adjoint of A. Then what about a determinant? The value of that matrix is called a determinant of a matrix, or otherwise the one row with the corresponding cofactors, multiplying one row with corresponding cofactors, summing all those values, we get determinant of A. So A inverse equal to adjoint A by determinant of A. This is the basic formula for finding A inverse. Next, based on this value, determinant of A value, we come across these two matrices, singular matrix and non-singular matrices. Singular matrix, what is the singular matrix? A square matrix, capital A, is said to be a singular matrix if determinant of A is equal to 0. If determinant of A is not equal to 0, then that matrix is called a non-singular matrix. Here, non-singular matrix only possesses inverses. The product of two non-singular matrices is also a non-singular matrix. If A and B are two invertible matrices of same order, then AB whole inverse equal to B inverse into A inverse. This is the one of the basic result in inverses of a matrix. Next, in the same way, if A is invertible matrix, then A inverse whole transpose equal to A transpose whole inverse. A inverse whole transpose equal to A transpose whole inverse. These two are same. So these four are the results, some basic results in the singular and non-singular matrix. Non-singular matrix has no inverse matrix. Singular matrix has no inverse matrix. Non-singular matrix is only having possessing inverse matrices. The product of two singular non-singular matrices is also a non-singular. If AB are two invertible matrices are non-singular matrices of same order, AB whole inverse equal to B inverse into A inverse. Next, A inverse whole transpose equal to A transpose whole inverse is also same. These are the basic properties. Next, we want to come across unitary matrix. This is one type of orthogonal matrix, one type of matrix which is applicable for a complex matrix, that is called a unitary matrix. A square matrix capital A is said to be unitary matrix. A power theta into A equal to A into A power theta equal to I, identity matrix. Then that matrix capital A is said to be unitary matrix. Now we have to remember the orthogonal matrix. What is orthogonal? Anyone can spell it? What is orthogonal? What is orthogonal matrix? What is orthogonal matrix? Okay, A into A transpose equal to A transpose into A equal to I, then that matrix is called orthogonal matrix. In the same way, unitary matrix is applicable for complex matrix. A power theta into A equal to A into A power theta equal to I. That means that what is A power theta? A power theta is A bar whole transpose or A transpose whole bar. that is nothing but the conjugate transpose of a matrix. The conjugate transpose of a matrix is called uh, the unit is called the matrix. That matrix, a conjugate transpose of that matrix, that is denoted by a power theta. A power theta into a is equal to a into a transpose a power theta equal to I. The transpose of unitary matrix is again unitary matrix. So that is, let A be a unitary matrix, then A transpose a power theta into a equal to I. Then a power theta in a power theta whole power a power theta into a whole dash, that is nothing but transpose equal to I. A power theta into a whole transpose equal to I transpose. That is nothing but by transposing properties, A transpose into a power theta whole transpose equal to I transpose equal to I. That's why this is nothing but A transpose whole power theta equal to I. Then hence A transpose is also unitary matrix. This is the basic result in orthogonal unitary matrix. Next, the inverse of unitary matrix is again unitary matrix. Now, let A be a unitary matrix, then a power theta into a equal to I. A power theta into a whole inverse equal to I inverse. I inverse is equal to I. That's why by the properties, basic properties of inverse matrices, product of inverse matrices, this can be reduced as A inverse whole into a power theta whole inverse equal to I. That is nothing but A inverse into A inverse whole power theta equal to I. So this shows that A into A power theta, that means that A inverse is again a unitary matrix. So the inverse and transpose of unitary matrices are unitary matrix. This is the basic concept about unitary matrices. Next, what about a rank of a matrix? From this, we have some important concepts. Suppose if A is any matrix of order n by n, a non-zero matrix, if you want to say the rank of this matrix is R, every R plus 1 determinant order every R plus 1th minor is 0, and at least one rth order minor, that means rth order determinant A is non-zero, then the rank of a matrix is said to be R, is R. So suppose, for example, if you consider this matrix, a 3 by 3 matrix, find the rank of this matrix 1, 2, 3, 3, 4, 4, 7, 10, 12. The rank of this matrix is said to be 3. Find the determinant of this matrix. The determinant of this matrix, det of A equal to this one. Determinant of A equal to, expanding this determinant by using first row, we get 1 into 4 12s are 48 minus 40 minus 2 into 3 12s 36 minus 28 plus 3 into 30 minus 28. Based on that, 8 minus 16 plus 6, that is 14 minus 16, that is equal to minus 2. So here in this case, minus 2 is not equal to 0, then determinant of A is not equal to 0. What order determinant it is? Third order determinant. That's why the rank of this matrix is row of A equal to, this rank of the matrix is denoted by row, and the row of A equal to 3. So it is a non-singular matrix of order 3, hence the rank of A equal to 3. So based on this, every minor of order R plus 1 must be 0. At least one minor of order R is non-zero. Then the rank of that matrix is nothing but R, and it is denoted by rho, and rho of A equal to R. The rank of a matrix is always unique. Always unique. Every matrix will have a rank. Rank of null matrix is 0. Rank of identity matrix is the order of identity matrix. Suppose if you have 3 by 3 identity matrix, that is the order of the rank of that matrix is 3. If you have 4 by 4 identity matrix, we have the rank of that matrix is 4. Like that, we have to say the rank of identity matrix is the order of the matrix. Rank of null matrix is always 0. The rank of non-singular matrix of order n. The rank of non-singular matrix. What is the non-singular here? Determinant of A is not equal to 0.